Right, so let's talk about affirmative action. This is going to be a highly simplified view of where we're going with this. So imagine we have our two groups, S and T, and intuitively, we're going to, in this particular example, have the same number of people in S as I have in T. It's highly stylized. And imagine that, we have distances for every person in S to every person in T. And intuitively, what we're going to do is we're going to pair up members in S and members in T so that we minimize the cost of the matching, the sum over I of the D of SI to T and the person that SI was paired to. And then what we will do is we will classify individual S by simply classifying the partner T and taking that to be the outcome. So this is going to be the general shape of what's happening. And we'll talk about why we want to do this and so on in a moment. Well, maybe I should talk about it now. No, not now. Okay. So before we get to kind of how we're going to be using this general intuition, I want to talk to you about another notion. Suppose we have two distributions. You can think of them as being on the same set, or you could think of them as being on different sets, but where we have a notion of distances between elements in this set and elements in that set. It doesn't really matter. The way we're going to be using this in the future is we're going to be talking about the uniform distribution on people in this set and the uniform distribution on people in that set. So there is a notion of distance between them, and they are disjoint sets. But it doesn't really matter. Okay, so suppose what I want to do, we're going to need a new notion of distance between distributions. And some of you will be familiar with this. So here I have these are distributions on the same element, the same set of elements. This distribution assigns a weight of 1/10 to Y and 2/10 to X. This one assigns half to Y and 0 to X, and so on. And these numbers all add up to 1, and these numbers all add up to 1. And I want to take this distribution on the left, and I want to convert it with a kind of minimal effort or minimal mushing around to the distance on the right, the distribution on the right. So here is a picture of my two distributions. So here's Y of a half, that looks much larger. Here X is 0. Here X is 2/10, and so on. So these are just different. Think of them almost as skylines, two different possible skylines. Now, I want to transform one to the other. And I think of these like as clay shapes. I have a clay skyline on the left, and I want to convert it by mushing the clay around to the skyline that looks like the picture on the right. And the cost of moving will capture the differences between the distributions. So how do I do this? Well, it costs 0 to move a unit of clay or a fragment of clay from Y to itself. That's right. And in general, if I have a metric, D of XY, that's what it's going to cost to move a unit between X and Y. So this is, of course, the earth mover distance. That I have, a shape of piles of earth here, and I want to reshape them over here. And so what is this? The earth mover distance is captured by a linear program. And I think of the function h as the hauling function, telling me how much dirt I'm moving from X to Y. And so the cost of moving this much dirt from X to Y depends on how much I'm moving and how far I'm moving it. And so I want to minimize my total hauling distance, hauling costs, hauling times distance, so that I'm starting here. The stuff that's coming out of S if I look at X, which is in S, and I have a certain amount there, and I'm moving this now to various people in Y, the total amount that I can be moving is just X. So I sum over all the Y's of how much I'm moving from X to Y, that's just S of X. And similarly, the stuff coming in to Y is I'm summing over everybody how much I'm hauling from X into Y, that has to be at most T of Y. And the hauling amounts are never negative. Okay. So, good. So I have now this notion of transforming one distribution to another. And suppose really that I'm doing this by working with clay. And in my distribution on the left, half of my clay is pink. And I'm reformulating this to give me the distribution on the right. Then of course, half of the clay on the right is pink as well. Or the other way to look at it is, if when I'm done, half of it on the right is pink, then again, half of it on the left must have been pink. So you can think of the pink people as the people who are getting a classification outcome as 1. And I'm going to be looking at mapping individuals in S to individuals in T in some sort of a fair way, and then giving to the member of S the classification of the person that it was mapped to. So if a third of the people in T are going to be accepted to whatever, then after the mapping, a third of the people in S will also get accepted, because they got mapped to, uniformly into T. We're covering all of T. So, yeah, this is right. Okay. Good. So, again, if half the clay on the right is pink, then half of the clay on the left is pink. So that's going to be a notion of what we're calling fair affirmative action. We have 2 different groups, S and T, and we are going to map the individuals in S to individuals in T, and the mapping is going to satisfy the constraints of the earth mover. It's going to be a minimization, as in the earth mover linear program, and we're also going to require the Lipschitz constraints. So that means that similar people here in S will be mapped to similar distributions here in T. Now, why did we map from S to T rather than from T to S? No particular reason. We could have done it the other way. There was a lot of talk a number of years ago about minority populations that were not known well to the businesses. Like, the banks don't know this subpopulation. So there was some sense in which the banks might have a very refined approach to deciding loans for people in T, and maybe they just didn't know the subpopulations S1, S2, and so on and so forth, and it made some sense to map from S to T. But nothing really insists on this. So the idea is, again, we're going to map uniform distribution on S to the uniform distribution on T via the earth mover LP, while also satisfying the Lipschitz conditions. And then we classify T as we would have. So again, we'll have now statistical parity. That's the pink clay argument with the earth mover. And we have individual fairness within S, and we have individual fairness within T. but we no longer have individual fairness between members of S and members of T. And we're going to discuss that, but there's a question.
I just find it a bit strange that you're mapping S, which is a particular population, to T, which could be completely different.
Right.
So when you do the Earth moving, could you have like massive distance between the two populations?
Right. You could have massive distances, and the Earth mover will just try to minimize the total amount of change. But yes, you could have big distances.
But does that mean you still have fairness? When the individuals you're moving over are actually not very similar.
The individuals you're moving over are not what?
Very similar because of the massive distance.
So, I'm sorry. You mean whom you're being moved to may not be similar to you?
Yes.
Good. So hold that thought, because I said we're going to violate the Lipschitz conditions between S and T, and we're going to talk about that. But we haven't. You're absolutely right.
There may be no maximum minimizers for your Earth mover distance that are remotely Lipschitz, right? Because
yes, and so you're going to try to minimize, and you're going to. Sorry.
So when you say you minimize,
we're going to insist on Lipschitz between elements of S. But
I mean, imagine for a second that S and T have the same number of people, right?
Yeah.
And the solution in the Earth mover thing has to be permutation, just because it's an extreme point.
No, it's no.
Linear programming.
Hold on. I may be using the wrong language, but let me say the following: in the situation that you're talking about, could I take each element of S and completely uniformly have them choose an element of T?
No, because you'll be minimizing the Earth mover distance
right.
over
okay.
all
Good.
of your
Good.
transportation plans. Then the permutations are extreme points, so the maximizer will be always in permutation. The minimizer will always be a permutation.
Okay.
And if the metric on T is such that all distances are far away from each other in T, any permutation that maps S into T is going to have a huge Lipschitz constant.
It's going to have a huge Lipschitz constant between.
Meaning that things which are close in S.
No, I'm sorry. I'm missing something here. I don't understand.
But I'm just saying,
I can't understand why, for the purpose of fairness between elements of S only, I can't insist that each person in S is uniformly mapped to somebody in T.
Because this can never be an optimizer to linear programming if you insist on optimizing just the Earth mover distance.
So I'm going to insist on the Lipschitz constraints, and I'm going to do the best that I can on the Earth mover.
So you are not optimizing. Okay, I understand. Okay.
Yeah.
So you're in the optimization, you are softening the Earth mover
right. Best efforts conditioned on the Lipschitz conditions. Thanks. Okay. Good. So, thank you. Let me just remember where I was. Right. Good. So when we do this, we're implicitly reweighting the loss function. I'm sorry. We want to reweight. We might choose to reweight the loss function L that we use for our optimization here in the fairness LP. If you remember, we're optimizing subject to the Lipschitz constraints on the elements of T. So let me back up, because I think I got interrupted and missed one thing in the flow. So what's the procedure here? We're going to somehow be mapping the guys in S to T, and then we are going to be using the old fairness LP to assign probability distributions on outcomes to the elements in T. All right, so that's where our fairness LP is. That fairness LP had loss functions. We had assumed that there was some loss known for taking an individual V and mapping it to an outcome O. When we play this game of kind of saying somebody in T is no longer just somebody in T. They're also now representing some spread on the population in S. So it makes sense that we would maybe reweight the loss function. And so for every Y here. And for every outcome, our new loss is going to be defined as the sum over all x and s of the probability that individual x here is mapped to this particular y, times the loss function incurred by mapping that y to the outcome O. So we're saying, hey, t is now a representative, and the actual loss of mapping it depends in part on like how much or what parts of S it came from. And again, this mu x is what we got from our Earth mover and Lipschitz mapping that we did between here. And again, now we're going to run the fairness LP, but using this reweighted loss function. Okay. So, what's our sort of new problem then? We're going to, we end up with the following distance. The distance like in how S is treated and how T is treated is the minimum over X and S, and Y that is drawn from the distribution that we have assigned to X of D of XY. And we want to minimize this such that the difference in the distributions that are given to individuals in S should satisfy the Lipschitz constraints on these two elements in S. And then the total variation distance we want to be bounded by some epsilon. And here mu sub S is defined as for every y in T, it's the chance of landing at y if we choose an element according to S. Okay. And then these are the distributions. Mu x are the distributions on elements of the outcome set for guys in X, in T. That should say for all X in T. Okay. No, stop me. Stop me. Mu x is the distribution on elements of T for anybody in X. Okay, good. Okay.
So the Lipschitz constraint only enters on the level of distributions, right? So
well, we are insisting that, yes, that the distribution of where X is mapped in T, for two people, X and X prime in S, we want that their distribution on where they get mapped in T should be similar. We also, right, okay, and then we will also, when we run the fairness LP, we're going to be insisting that for two people in T, the distribution on outcomes that they will experience are similar, bounded by their Lipschitz.
You're saying is that this function h, that you have this function h way before, it satisfies that it's Lipschitz viewed as we put L1 norm on the y's.
Y's are in
Y's
T?
in the destinations.
Yeah. Yes.
How does this prevent us from accepting those who look like accepting those S's that look like?
Great. So the question is, why is this different from just accepting those S's that look like members of T, members in the minority group that look like the majority group? And the answer to that is, so the answers to essentially all questions along these lines is always the same. Everything depends on the metric. We're assuming that the metric is truth, D of XY. And so we're minimizing true distances to the best of our ability. So that is supposed to be completely orthogonal to hairstyle, or other ways in which members of the minority might or might not look like the majority. Yeah.
If I understand correctly, the difference is what she was asking is that here you allow a person in S to be viewed similar to a number of people in T. So then you're sort of averaging the outcomes of these people to get the outcome for S, for X and S.
This is true, but in some sense, we are allowing a best effort similarity between somebody in S and somebody in T. We're not observing the Lipschitz constraints between S and T, only S and S versus T and T.
Right.
So let me just follow this example just for a second. If I have two people in S who truly are similar, and one of them happens to look very much like the majority, and the other one happens to look very much like not like the majority, because they are similar in S, they must be mapped similarly to their distributions in T. So they are treated similarly. They can't be mapped like this. They have to be mapped similarly. Yeah. What if you don't have what?
A representation in T that is similar to the minority that doesn't look like.
What do you mean by a representation?
A particular set of features that is typically only seen in minority. It's just really hard to
Great.
see.
Okay, so now we're coming back to the question of representation. So, as I said, in the early work, we were actually assuming that the representation was super rich and detailed so that you could find all the information you actually need. The very real and very compelling question of what happens when the features are differentially expressive in different groups and so on and so forth, that has to be addressed. And as I will tell you more than once, my dream is that is that we can figure out how to design algorithms where when the question is, build a fair this or build a fair that, the algorithm looks at the data and says, are you kidding me? With these features, this kind of data, there's just no way, I'm not doing it. So I don't really sign on to the, yes, we're just going to do the best we possibly can. Algorithms have to say no. But we don't know how to design them in a way yet that say no under the right circumstances. But usually when I talk about this, I give this as the primary open question, is how to figure out when the algorithm should just say no. And say, forget it, go out, pay more money, get better data, and then come back to me and I'll try. Yeah, so it's a very good point. Yes?
Is it possible, is the scenario possible, assuming the metric is true, as you said, is it possible that S for people to be very similar but look like a majority? And like you said, very similar but one belongs to...
So sorry, I have a problem, I don't even know what look like means when we have access to the true distance D. Look like is irrelevant because the true distance D is what we're using to try to control things.
Right. The question I'm asking is, the premise somehow of my sort of misunderstand is you said when he asked the question that people in S could be mapped differently, but if they are similar, they'll be mapped similar.
To similar distributions.
And I'm saying, when is the premise ever true? If we have a true metric, aren't similar people in S also always similar in T?
I don't know. What does it mean to say? They are not in T, they're in S. These are two separate subgroups of the population.
I understand, but I'm saying, is it possible ever for two dissimilar people in S to be mapped to a similar?
Absolutely. Absolutely. The fairness requirements only say that you can't exceed. The difference in distributions between X and X prime cannot exceed the distance, the true distance between X and X prime. It doesn't say it can't be smaller. So, for example, maybe just everybody maps to one person in T all the time.
But that's not possible given your uniform distribution.
Good point. So everybody chooses randomly with one oversized of T.
Everybody's mapped to uniformly random person.
Yeah. So those are identical distributions and much, smaller than the true distance. The difference between them is 0, and the true distance might not be. More questions? Yeah. Not yet.
Can you say again what the definition of a capital case of x.
Capital D of mu x and mu y? Great. That is a distance in distributions, capital D. Yeah, it could be, if that's what you're using for your definition of fairness. It should take the, yeah, that little d of x prime is the metric.
I'm saying, I feel like capital D.
You're thinking what?
I feel like capital D should take the metric on y, or the metric.
I don't understand. Capital D is any notion of distance on distributions. So I don't, you know, like total variation distance, it doesn't make sense to say total variation distance has to take true distance into account. I'm not understanding that. I'm having a type mismatch.
I guess, like, for example, x and x prime are very similar, but they get matched to completely different distributions. One that puts all weight on like one y and t, and one that puts all weight on y prime and t,
right.
where y and y prime have very close distance, and that's still like okay.
Oh, I see. You're saying we're being overly conservative, overly cautious. Good. That might be true, and it might be possible to do better. That's an excellent point. So we're being really careful. Guy would probably say we're using the triangle inequality. Yes, but you're right, Daniel, that it might be possible to do something better. Good. Okay. So, oh, sorry.
Are we using the same distance metric for the S and T?
Same, yeah, D is a distance metric for the union of S and T. So for all people in the universe, which is the union of S and T, for all pairs of people, that's D is the same D. Little d is the same D.
Not to the truth, maybe the minority don't have some features, and if you just measure distance based on one single feature.
Again, this metric is supposed to be capturing truth. And the representation problem is a major open problem, and we don't address it here yet. But we'll talk about it again tomorrow, I promise you. Yeah. Okay. Yes?
Practically, how should I be thinking of
what?
S and T? Practically, how should I be thinking of the classes S and T? So I think what's tripping me up is, say, I consider S to be the group of women and then T to be the group of men.
Okay.
The mapping is going to be very difficult in certain cases.
The mapping is going to be what?
The mapping from S to T in certain circumstances is not going to exist, or it's going to be extremely challenging.
Why? Assume that we have a distance. So again, the magic is always going to be in the metric. So if miraculously we have a well-defined distance between all pairs of people, whether those pairs are the same sex or different sex, the same gender or different gender, doesn't matter. If we have that, then we can do this. Finding the metric is, of course, what Guy was talking about yesterday. Right. Good.
Even though the system makes sense, it seems like this looks very different than how I imagine affirmative action as it currently exists.
Good.
And that it seems like you could take some members of S and give them a huge boost, and take another member of S far away and give them a tiny boost.
If they're far away, they're truly distant for whatever it is that the true metric that matters for this task.
That one makes sense, but it seems like I would imagine affirmative action is you take everybody in the group and you give them like a uniform boost.
Well, this is why we called it metric fair affirmative action, because we want the metric to play a role. We think that that helps.
I see.
Okay?
Thank you.
Great. Other questions? I really like the way you guys are probing the definition. And you're uncovering exactly where everything is difficult. The design of the metric, where does that come from? Where do the features come from? How do we get a good representation? This is where your questions are all converging, and you're totally right. I don't see any more hands. Of course, there's this light staring me in the face, but okay, then we'll go on. Good. So here we have assume that we're given now. I'm just spelling out what we've been saying. We have mappings from individuals in S to distributions on T. And we have the mappings from our fairness LP taking individuals in T to distributions on outcomes. Okay? So the overall mapping is going to be as follows. When I want to classify individual X, if X is in T, I take a draw from this distribution that was given to me by the fairness LP between here and the outcomes. If X is in S, first I choose somebody in T from my distribution on T that I built up over here. And then I do exactly what I just did for that person in T. So that is the approach. So let's talk about it a little bit more. I think that it minimizes loss. And because of the fairness LP, it's minimizing some kind of loss. It's also trying to minimize the disruptions of the S cross T Lipschitz requirements. It is not strictly adhering to those requirements, but the formulation of the earth mover distance that we use discourages long distance hauling, at least for large amounts of mass. And it's also giving us the parity constraints because we're taking uniform to uniform. So, and finally, it is maintaining the within group Lipschitz constraints. Now, what did I write here? Good. So I suggested 2 slides back a reweighting of the loss function. It's not the only possible reweighting. There are other reweightings that could make sense, and you might want to use them. So, for example, one possibility would be eliminating the reweighting. And that means that when the fairness LP is running, everything involving S is just immune. It's like invisible to it. Because it hasn't changed the losses, and that's the only way that S can affect that thing. So that may make sense. Remember I mentioned this scenario that we kept hearing about. Oh, the banks aren't giving loans here because they don't know this subpopulation. Now, by the way, quick comment. I'm not an expert on these things, but my understanding is that it's not out of the question for a country's economic policy to do something like give banks tax credits for giving loans to subpopulations doing exploratory loan giving in order to learn more about a subpopulation. I have heard these things said. I don't know whether it's not my expertise. But it's really good to sort of question the fundamentals, check the ground rules, and see if there's any room for them to give. Okay. Now, let's see. So one thing that we could have done is we could have just, instead of going through all of this mapping S to T and then whatever, just maybe slap on statistical parity as a requirement. So take the original fairness LP applied to the union of S and T, and then in addition add a statistical parity constraint. This is doable. If you compare what we chose to do to that approach, we have more faith here to the S cross T distances through the, if you look in the paper, you see some very, very weird things happening that don't happen in this case. And we end up providing protection against this sort of self-fulfilling prophecy that I might have talked about in the catalog of evils, in which one deliberately selects the wrong subset of S and then says, see, these people didn't perform. So this gets ruled out. And again, as has come up in the discussion, the metric is everything. So a different approach would be, rather than changing the loss function, try modifying the metric. It's a different philosophy. It's just a different philosophy. But it also captures a different point of view, which says, yeah, there is a metric here, but the metric isn't taking into account somehow the reasons for why, this person is in this group is more likely to have a positive outcome than this person in this group. Meaning that maybe the reason for this difference is sort of is a history of discrimination or lack of resources for this person compared to what this person has. Now, that actually brings up a really important question about the metric. And I have some slides somewhere, but I don't think they're in this deck. Think about hiring. So let's suppose that we have a news organization. Yes, this is ripped from the headlines a couple of years ago. We have a news organization which has a history of harassment and very poor treatment of women. And suppose our definition of success on the job is once you're hired, within 2 years you get a promotion. You stay there for at least 2 years and you get one promotion at least in that time. So if we look at similarly qualified and talented individuals, it may be that the chance of success at the nasty news corporation for the man and the woman are different because of the hostile work environment. What should the metric be capturing here? Should the metric be capturing that environment? So if two people are dissimilar in their probability of success in this job, for whatever reason, then the metric should say that they're different. Because, it is the truth, right? This is what will happen. Or should instead somehow the metric be capturing what happens at nice news corporation, where everybody is supported and enabled to reach their full potential, or encouraged to reach their full potential. So again, everything is in the metric. That's where all the cheating is. But it's also where you can set the ground rules and say, follow these rules. And we don't have the answer here. This is something you have to work with. All right. Just a comment which you probably have all figured out by now. This mapping here will satisfy statistical parity between S and T up to however well we manage to solve the Earth mover, minimize the Earth mover distance. And it'll satisfy the Lipschitz condition for every within group pair. And we've discussed quite a bit why that's true, secondly. Okay, so that was a discussion about affirmative action with one minority group using metrics. And we can handle multiple disjoint minority groups using the same approach. So if you, in fact, split your sets according to social strata and zip codes and things like that so that we actually get disjoint sets, you can apply the same algorithms to each of them independently, and it's not a problem. Okay, so we know how to handle it with a metric. What about the intersectional case? By saying zip plus 4s and blah, 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 I forced my groups to be disjoint. But what if your groups are, on the other hand, non-binary individuals and African Americans, and this is intersectional. These things don't say anything yet. How do you handle this? We're not going to answer that yet. But it does, we're just not going to answer that yet, but we'll probably come back to something about it. Maybe not. Sorry, maybe that's the end of the line on that. We'll see. So the next thing I want you to think about, and I think this might have been implicit in one of the questions earlier, is what we'll call fair affirmative action via rankings. So what are some examples from real life of this? The University of Texas school system, the University of California school system ensures that within every high school class, the top 10% of the students will get admission to at least one of the respectively University of Texas or University of California campuses. By doing this as top 10% of students in each high school class, the high school classes are disjoint, and so we don't have intersections. Here's another notion, and this may seem strange at first, and I encourage you to think about it and read about it, and the more you think and the more you read, the saner it is. So John Romer is a very profound thinker. I think he's an economist at Yale. And he thinks a lot about school admissions and schooling in general. His general philosophy is to invest in disadvantaged people from early childhood in order to try to level the playing field. And this includes, if some of the children were born born drug addicted, and you want to invest a lot in these children in order to bring them up so that they can compete. And he views sort of younger children and younger people as less responsible for their what they have achieved. And the older you get, the more responsible you become. So he will be much more maybe oblivious in his choices early on, but much more demanding in his choices when it comes to, getting board certified for being a surgeon. And he's very, very cognizant of the dual roles of education, of both lifting up the underclasses by training people so that they can have high-paying jobs, and producing skilled workers for society. So his writing is just very deep, and he had the following proposal. He said, first, let's say thinking about college admissions, stratify the students according to the education level of the mother. And then within each stratum, rank each student by the number of hours spent on homework each week. This is very unintuitive at the beginning. You think, oh, well, if you're really bright, you don't have to spend any time on homework. But that's not the case that you should be focusing on. You should be focusing on, first of all, who has to work and therefore cannot work to support the family and therefore cannot study, or who has never seen studiousness modeled, ever. They don't even know that working, 10 hours, 12 hours a week on homework is a thing that somebody might do. And I find this completely compelling from a sort of personal perspective. I played the piano growing up. I started my lessons when I was 6 years old. I dutifully did my 30, 45 minutes of practicing. And then when I was 14, I went to high school, and I heard somebody playing the piano, and he was playing a Beethoven sonata, and it was gorgeous, And I realized that mortals, like people my age then, could actually play things like that. And my own practicing behavior changed dramatically, and I started playing 4 hours a day, and I got a whole lot better. It had never occurred to me. I didn't come from a disadvantaged background, but it had never occurred to me that this kind of thing was sort of something that would be done. So I found this extremely compelling. Okay, and then Romer says, once you have ranked the students within each stratum by the number of hours spent on homework a week, you admit to the university the top K%, whatever that K should be, to fill your universities from each stratum. A related example is from Danielle Allen at Harvard, and described in a paper called Talent is Everywhere. And her idea was stratify students according to their SAT scores or grade point averages or some other measure. And the only point of this is we're going to sort of get not super elite, but very good. Okay, so very good and who didn't score very well. I pleaded with her to randomize around the threshold. But in any case, and then she says, discard everybody below whatever your fixed threshold is. And then, having now focused on a different pool of applicants, you admit randomly in such a way as to maximize geographic diversity. And hence the title, Talent is Everywhere. Red states, blue states, whatever. Okay, so all of these are, Danielle's isn't exactly ranking, but she's kind of done a sort of ranking where she has the top and the not top. Okay. So, getting back, sort of summarizing this portion, we know how to handle multiple disjoint groups via the metric fair stuff. Without a metric, we could do it from a fair ranking. We don't know yet what to do about the intersectional case, but Guy is going to talk this afternoon about, not about evidence-based ranking, but about something from which we get to a notion of what we call evidence-based ranking, which does talk about assigning ranks and handling intersectional cases. I'm not going to say more about that. Guy probably is not going to talk about rankings, but you should know this exists, and we can, give you a pointer to it.
Remember to ask a question.
What?
Remember to ask a question.
Yeah. Okay, yes. Let me start here.
Isn't ranking some concrete application of a metric? Because metric is a very abstract idea, but ranking is more like simplified, concrete.
So a ranking doesn't give you a metric, but if you have a ranking, just like with Cristina Ilvento's work, the ordering of the points from the representative R doesn't tell you anything about absolute distances. But if you get distances at a few different points, then you can figure out something about the distances for people who are in between those. So the ranking gives you an ordering, but you don't know whether the ranking is like this, or it's like this, when the possibilities are all up here, or shifted. You don't know where it is, you don't know its spread. The numbers, right? Scorings give you rankings. Rankings plus some samples, some random samples will give you something like scores. But, yeah. Yes, Dimitri.
Sectional case. You can easily handle also, rather than individual people, you can handle random people for your Earth Mover setup, right? You don't have to have... So couldn't you do some intersectional thing where you, instead of taking kind of uniform distributions, you think of people who are kind of 50% viewed as if they're an S and 50% viewed they are an R?
That's a nice suggestion. I don't know. It's a really nice suggestion to think about. I'd like to think about it, but I invite everybody here to do so.
Maybe I don't know if people heard the suggestion when you spoke, so maybe...
Okay, so thanks. The suggestion is, actually,
Thanks. So for the intersectional case, I was just thinking that for the setup of the problem, you don't need to talk about deterministic individuals in the set S. You could talk about random individuals in the set S. So then you could imagine treating people who are in the intersection of S and R as being half the time in S and half the time in R, and then view them as random, and then trying to set up the same problem. I don't know if it works, but...
Okay, so you've heard...
Maybe something to say about that is, suppose we have two groups we're trying to protect, S and R, we have an individual, and the individual is in the top 10% of S, but somehow the bottom 20% of R. Who do we match them to? The reference population, what is the right thing to do? I don't know the 50-50.
Right.
So these are good questions.
Right, that was exactly what I was going to pick up, like what should the weighting be? But the idea that maybe you could do something like that, it's not obviously crazy yet. Good. Yes?
So a lot of the strategies that you were talking about introduce some notion of randomness into the decision-making process.
Yes.
How would you go about, talking about the psychological effect that has on people, right?
Great. So how do we talk about the psychological effects of randomness on people? So, I haven't a clue. Now, I heard from Rakesh Vora an example. I'm not sure I can reconstruct it. It had to do with lotteries for getting students into magnet schools. And the idea of assigning people randomly, a priori, in, out, using some, you have this many people and you choose a random subset of a given size. They didn't like that at all. They wanted a lottery. Even though mathematically it's identical, they wanted a lottery. So I have no clue how you're supposed to deal with that. Anybody have any suggestions? I really am very, very curious. We should talk also about arbitrariness versus randomness. And arbitrariness versus unfairness. I'm trying to decide whether we should continue with this discussion or I should go to the next content. But I think I should continue with this because there's only 5 minutes left. So, thought experiment. Hiring manager just has a thing about names that begin with C. They just hate names that begin with C, and they're not going to hire anybody whose name begins with a C. Period. Is this discrimination? Question 1. Okay, there seem to be people who think it's discrimination. Is it unfair? It feels unfair. Is it wrongful? Is it morally wrong? What was that?
It forces people to change their names.
Forces people to change their names. Well, but what if it's just one hiring manager and we don't have the so-called algorithmic Leviathan where all the decisions are made by the same nutty program that hates the names that begin with C? So is it wrong? Is it unfair? What is it? It's weird. It's arbitrary. It's kind of obnoxious and stupid. It may hurt the hiring manager in the long run more than it hurts the candidates. So what was that?
Is it known?
Is it known?
So that person can take action and change their name?
Great. So can you get this person fired for being so arbitrary? Or can you change your name in anticipation, right? I have no idea. Let's say it's not known for now, okay? So the legal scholar, Deborah Hellman, would say this is really arbitrary and really stupid, but it's not unfair discrimination. It's clearly discrimination. A discrimination is being made that people whose names begin with C are being treated differently. But her point is that it doesn't exacerbate any sort of systemic, like previous unfair treatment. And so it's discrimination, but it's not wrongful. And she has a book called something like When is Discrimination Wrong? And you can sort of ponder this kind of question. Yes?
But what if the letter C is chosen because Asian Americans are more
Right.
likely to come
Right.
back?
What if it's last names that begin with Z that they decide they don't like? That would be heaping on, jumping onto previous unfair treatment. Like, whether something is unfair or not, or wrongful or not, it depends very much on the context. Being told to sit in the back of the bus means an entirely different thing if it only happens to be the case that there is a seat in the back, rather than if you are being chosen to go to the back because of how you look. Yeah. Or specifically, if you're a woman on a religious bus in Israel, where the men don't want to see you. You're distracting them, so you have to go to the back. Wait, Kendra.
If I start a new form of discrimination, then by definition it doesn't have a historical precedent.
Right.
But that's true of all new forms of discrimination.
Right.
So
That's right.
that would still be unfair, right? The first racist person was still racist.
You're absolutely right. And so you're saying that Deborah Hellman is missing the genesis, and we do know that so Jill Lepore, in her book, We Hold These Truths, talks about systemic racism as America's original sin, and she talks about it being invented ex post, sort of to justify slavery. So you're saying Hellman is all washed up because this was some new thing, and there wasn't a history. But of course, this new thing was definitely heaping on past unfairness. And so I like your point, and I don't know sort of how to operationalize it. Yeah.
Can I make 2 points?
Sure.
One is that I think there's a lot of, so about your randomness, how people are handling randomness, one of the questions. So I just want to tell an anecdote. When people apply to UCLA for undergraduate admission, or people apply to Harvard for undergraduate admission, the chances are probably similar. UCLA gets like 160,000 applications for, 7,000 spots. Nonetheless, people are much more upset about not getting into UCLA than they're not getting into Harvard. And I think this is because each one of us has a certain internal expectation of what's the likelihood of something happening. Right? So when there's a big mismatch between our internal expectation of what's going to happen, that causes problems. So same thing with your Charlie or C for manager positions, right? We have the internal expectation that shouldn't matter, and when it does, people are upset. So it gets into very strange kind of closets of human psychology and perception of risk and things like this, which I think are much less understood mathematically. My second point is that there is an example where names matter. I'm sure that in show business, for example, or in politics, it's important to have a certain type of name, as we know from the evidence that people change there. And you could argue that fairness there is that, well, it's kind of your choice how to be named. You can change that. So it's okay, right, if there are kind of built-in mechanisms in that industry to discriminate against this or that. I mean, I would never make it with my last name, right? Forget it. But then you could say that because you can do something about this, it's fine. But if it's the color of your skin, you can't do much about that, right?
So let's just talk about, everything you say is true. Let's talk about one aspect more. You could change your name. So what is this famous study? It's like John or Jamal. So you could change your name, but if it feels to you like you're annihilating your own culture, What does it mean that you could change your name? At what price? And now we're getting into members of the minority who look like the majority, and we're kind of buying into it. So somehow that's the wrong direction. But yeah. Okay. Yes.
Cynthia, I just want your views on what labels you would attach to the situation in the Wimbledon tennis tournament that just finished, where the organising committee banned Russian and Belarusian players from playing.
I'm sorry, I'm not going to comment. I haven't given it any thought whatsoever. I didn't even know this had happened. I'm sorry. I don't want to give an answer when I haven't thought.
Sure. Just your example of the manager.
What was that?
Just your example of the manager that doesn't like the name C.
Right.
C sparked that for me.
Mm-hmm.
So it's just a real life example that's just happened.
Okay.
Which is up for grabs.
But it wasn't Russian names, it was people from Russia. Yeah. Anybody else want to comment on this? Give an opinion? I don't have one. I mean, I just haven't given it any thought whatsoever.
The woman that won from Russia but moved to Kazakhstan, the Russian one.
What happened?
The woman that won the Wimbledon was from Russia but moved to Kazakhstan a couple years ago.
I see.
Right.
Okay, I think if there are no other questions, then we can stop. Okay, good.